your entire screen, share, and now comes up my board here, camera. All right, do you guys see the lesson outline?
I can see it.
See it.
Yes.
You can see it? Is it clear?
Yeah.
Okay. All right, we're going to start. First lesson. All right, so our learning goals are to find the slope of the tangent to a curve at a specific point using the underlying idea of calculus. And we're learning the difference between a secant and a tangent. So what is calculus? It's different from anything we've done up till now. It's cool. Both things we're going to do, calculus and vectors this year, aren't just things we've kind of done before. They're completely new, which makes it interesting and different and kind of like a fresh start for everybody. So two simple geometric problems led to the development of what we now call calculus. The first one is, what is the slope of a tangent to the curve y equals f at x at a specific point? And this is differential calculus, which is what we focus on in grade 12 calculus, okay? And what is the area under the curve? So this would be the area under the curve, y equals f at x from x equals a to x equals b. This is integral calculus, and this is what you'll get into in first year after they do probably 2 weeks on derivatives, all the stuff that we will do in this year. So slope of the tangent to the curve at a specific point. So I did a little sketch here for you. So here's our specific point P, and then here's this thing called a tangent. So a tangent is a line that touches a curve at only one spot and best resembles the slope of that curve at that specific point. So it only touches it at one point, okay? I call it like kissing it, like just kissing it and off. And it best resembles the slope of the curve at that point. You may have, if you've done physics, you've seen tangents before. So here's our important definition. A tangent is a line that touches a curve at a single point and then best resembles the curve at that point. So I got some pictures off of Google Images that show tangents. In our first picture here, we've got a tangent, a horizontal tangent, which is important because that's where the slope of the tangent is 0, horizontal tangent. And why that makes sense is you can see this curve here. If I were to draw a tangent in, say here, it would be fairly steep. And then as I get closer to that minimum there, I'm going to get less steep by drawing a tangent. And I would keep getting less and less steep until it makes sense at this minimum here to have a horizontal tangent or a slope of a tangent that would be 0. And then also you can see in this example that here the tangents are all decreasing until we get to this minimum where we have a slope of a tangent at 0, or they're negative slopes if you think of it that way. All right. And they're also getting less steep to, or sorry, more steep to less steep. Then on the other side, we have positive sloping tangents, and you can see they've shown one up here that's not quite at the maximum. Before the maximum, still we have a not quite steep, but a positive tangent. And then those would keep getting smaller and smaller until you get to the actual maximum, where again, you'd have a horizontal tangent. So there's our, and then it's also showing here, here's a tangent drawn in, and it's giving you that idea that if you wanted to get the slope of the tangent, you would need the rise divided by the run. Shows a little rate triangle in there for you. In the second example I took from the internet, it just shows a curve with the tangent drawn in. And remember, again, the tangent touches at one spot and best resembles the slope of the curve at that point. And then in the third example, I drew in, or I picked this one because if you see here, at this point, this line is tangent. And we always harp on the fact that it can only touch the curve at one spot. But so right here, we're tangent to the curve at that spot. But over here where it crosses through, that's just an extension of the tangent line. It's not tangent to the curve at this point. Obviously, if we were going to draw a tangent here, it would have a positive slope and look something like this. Okay? So it's tangent here. It's just an extension of the tangent line when it crosses the curve later on there. All right, and then a secant is a line that joins 2 points on a curve. So this is a good image that I snipped where it shows a tangent line where it just touches at 1 point, but it also shows a secant line where it joins 2 points on a curve. And the difference between a tangent and a secant is important for the development of calculus, or how Newton first came up with how he was going to go about solving this problem of finding the slope of a tangent to a curve at any point. All right, so we're going to start off looking at a tangent problem that we could solve based on kind of grade 10 math without any calculus at all. So in grade 10, we learned that the tangent to a point on a circle is always perpendicular to the radius. You may forget that you did learn that in grade 10, or you may not have, depending on how much time your teacher had for analytic geometry. But it's true. And you can easily kind of see it's true if I draw a radius in here. Simple radius. There's my radius. And we can see that the tangent would be at this point here, would be straight up and down, which is perpendicular to the radius at that point. Okay, and it turns out that a property of circles is that the tangent line is perpendicular to the radius at any point on the circle. So here's the point they want us to focus on, the point 4,3. So I'm going to join the radius in there. So there's my radius. So if I want to know the slope of the radius, I could just easily make a right triangle here. You can see that it's a positive slope with a rise of 3 and a run of 4. And our slope of the radius is positive 3/4. And we know that perpendicular slopes are negative reciprocals. That's another blast from the past, grade 9 maybe. Probably used it a bit in grade 10 as well. So the slopes of perpendicular lines are negative reciprocals. So we know in this case that the slope of the tangent is going to be the negative reciprocal of 3/4, which is negative 4/3. So that means if I want to draw the tangent in to the circle at this point, I'm going to start at this point here and use the slope of the tangent and go down 4 and right 3. Down 4 again, right 3, well, that's off my page, reverse it, up 4, and left 3. And then I should have my points and I can draw in my tangent. So again, I've drawn in a tangent line here using a geometric property that I happen to know about circles. And it does look perpendicular, which was also a property that we're looking at. But again, looking at this tangent, it should be the slope of best resemble the slope of the circle at that point. Okay, the tangent that I've drawn in. And it looks like it does. Okay, so how do we find the slope of the tangent at a specific point if we don't have a geometric property like that to use? Well, we use calculus. So the following example outlines the procedure, okay? So this is kind of like the very first bare bones of calculus. This is how Newton came up with calculus, or this was his thinking behind it. So the following examples outline the procedure. So here's our problem. Find the slope of the tangent to the curve f at x equals x squared at the point 2, 4. All right, so hopefully you recognize this as the most basic parabola, y equals x squared, and I did a little handy graph of it there for you. And we want to know the slope of the tangent at this point here, 2, 4. So this is my x value and my y value. This is point P. So the first problem you run into if you want to find the slope of the tangent there, the exact slope of the tangent, not just approximating it, by looking at, like if I was looking here, I'd go, okay, well, how am I going to draw this in so it best resembles, and what's its slope going to be? But we want to know the exact answer here. We don't want to estimate. So the first problem you run into is to get the slope of a line, and a tangent is a line, you need 2 points, and we only have one. We only have the 1 point P 2, 4. So what Newton thought of was we're going to create a point Q, which is just going to be to the right of P. So here's my point Q, and it's just a little bit to the right. So here's my x value 2, and then if I look down here for Q, my x value is 2 and a little bit, and we're calling that little bit h. So the first thing we're going to do is set up our 2 points. So our point P we know is 2, 4. Our point Q, well, it's 2 and a little bit, and we want to call that little bit h. So our x value is going to be 2 plus that little bit h. Okay, so that's the x value. We want to know the y value that goes with x being 2 plus h. So this goes back to function notation, which we did in grade 11. So for instance, the way we got the 0.24 was because we knew f at 2 following function notation would be 2 squared, which would give us 4. So that's how we got the 0.24. And if I asked you what f at 5 was, you'd be able to tell me, following the function notation, you replace x with 5, it would be 5 squared, or 25. Okay. What if I asked you what f at 2m was? Does anyone remember how to do that from grade 11? Answer me. You can unmute yourself if you remember what f at 2m would be.
We would square the 2 as well as square the m, so it'd be 4m squared.
Right. So now my question to you guys is, what is f at 2 plus h? Where should I do that? I'll do it here. What would f at 2 plus h be? Anyone?
It would be bracket 2 plus h squared, and then writing that out would be h squared plus 4h plus 4. Perfect.
Awesome. Okay, so I'm going to write it out twice instead of going straight to that. But if you can square a binomial in your head, then that's totally okay. So for anyone that's rusty, so squaring a binomial, we have to write it out twice and then do FOIL or multiply the binomials together. So f at 2 plus h is going to be 4 plus, so that's 2 times 2 is 4. 2 times h is 2h. H times 2 is also 2h. And h times h is h squared. And then these are like terms, the two h's. So we get 4 plus 4h plus h squared, which is exactly what was said. So there's our 2 points. So there's our P, 2, 4. And then this point Q would have the coordinates 2 plus h, 4 plus 4h plus h squared. So our first problem we ran into is we only had 1 point, we needed 2, and we solved the problem by making Q be just a little bit to the right of P, that little tiny bit being h, and then substituting 2 plus h into our function to get the corresponding y value. All right. So we're going to left us room on the next page then. So the next step that we want to do is get the slope of the secant through P and Q. So I'm going to remind us then that P had the coordinates 2, 4, and Q had the coordinates 2 plus h, 4 plus 4h plus h squared. All right, so to get the slope of the secant, we're just going to do grade 9 math here. P is going to be our x1, y1, and Q is going to be our x2, y2. And the slope of the secant, which is the slope between P and Q, is y2 minus y1. It's our slope formula from grade 9 over x2 minus x1. And then we can substitute in 4 plus 4h plus h squared for y2. There's a minus sign in the formula there. Y1 is 4. Over x2, which is 2 plus h, minus x1, which is 2. So we just use this formula and substituted in x1, y1, and x2, y2. Now, if you look in the numerator, something nice happens here. We've got our 4 and our minus 4. And when we add those together, we get 0. So it's like a 0 pair. 4 minus 4 is 0. So we're just left with 4h plus h squared in the numerator. And in the denominator, the same kind of thing happens here. We have the 2 and the minus 2 that also add up to 0. And we're left with h.
Oh.
Now,
Miss Northwood,
yes.
how come you don't need brackets around like each one?
Like put brackets around this?
Yeah, why don't you need?
Oh, okay, that's a good question. So the only reason I would need brackets is if after the minus sign there was more than one term, because then the negative would be distributing over what came next, but I don't have that. Whatever comes first doesn't need to be in brackets unless there was a multiply, right? And then I've got my minus sign. Whatever came second would need to be in brackets if there was more than one term for sure. Or if the term happened to be negative, you would want to use brackets for it to look nice as well.
Okay, thank you.
Does that answer you? Okay. All right, so my question to you guys is this simplified as much as it can be?
No.
No.
No,
Yeah.
what could I do?
You could. Should I answer?
Yeah, sure.
Why? Okay. Because you can just divide the h out of both the terms.
Okay, so I could divide the h out. I'm gonna say common factor, but it's the same thing, John. So if I common factor h out of the numerator, I get, so 4h divided by h is 4. H squared divided by h is h. And then I've got h in the denominator. And we know from grade 11 simplifying rational expressions unit, that we can divide out those h's as long as h is not 0. Do you remember that? You can't, division by 0 is not allowed. Okay, so then we've actually simplified this slope of a secant down to just something really straightforward there, 4 plus h. Okay. All right, so all we did there was just set up. We haven't done any calculus yet, so now's the part where the genius came in and decided what we could do for calculus here. So Newton figured that the point Q, so here's my point Q again, could be moved as close to or as far away from P as we want, but focusing on making it closer and closer and closer to P so that it's pretty much indistinguishable from P. All right, so Newton figured that the point Q could be put as far or as close to P as we want. The closer it is to P, the closer the slope of the secant would be to the slope of the tangent. Okay. In fact, the point Q could be moved so it's so close to point P that it's virtually indistinguishable from P. So they're practically on top of each other. Okay. So in other words, Q can be moved infinitely close to P. This means that the horizontal distance h is going to be very close to nothing. Okay, h is going to close in on 0. It's going to get very, very close to 0. H was that little horizontal distance that we put Q away from P. So if you reword that, we say that as h gets closer and closer to 0, the point Q closes in on P, and the slope of the secant gets closer and closer to the slope of the tangent. And in math, we use the word limit to explain this idea of approaching or getting closer or infinitely close to something, to explain this idea. So Newton said that the slope of the tangent is going to be the limit. Limit is used with regular size, the regular size that you would make a number. As h approaches 0, that's written in kind of subscript, so smaller and below. And so the limit as this little distance h approaches, that's what the arrow means, 0, so it gets closer and closer and closer to 0 of the slope of the secant. Okay? So if we follow this through, the slope of the tangent in the example we just did is going to be the limit as h approaches 0. Well, this is the slope of the secant. So the limit as h approaches 0 of 4 plus h. So the slope of the tangent then is going to end up being, so now we're going to let h approach 0. So as h approaches 0, 4 plus h approaches 4. So that would mean that the slope of the tangent would be 4. And then we're going to go back to our picture and actually draw in the tangent line using a slope of 4 and see how it looks. So slope of a tangent again. So if our slope of the tangent turned out to be 4, which is our rise over our run, 1 would be our run. So from our point P, we would go up 4. And to the right 1, reverse it down 4 to the left 1, join our points, and we should have a nice tangent drawn in. So there is the tangent at the point 2, 4, and we know it has a slope of 4. Okay, so, and then I've got my asterisk at the bottom. This is actually like super, super important. So remember, h only approaches 0, but it can never actually get there. Otherwise, you'd be dividing by 0 up here, right? And we said we can't. We can divide by anything except 0 because division by 0 is meaningless, okay? So keep that in mind, that we're letting h approach 0, but it's going to get infinitely close to 0, but it will never actually equal 0. Okay, so that's kind of, those are the 3 steps. That was our very earliest kind of iterations of calculus. And that's what we're going to do today. Tomorrow, we're going to see how the formulas were developed for the first principles formulas. That's what we're going to do tomorrow. So taking this process and generalizing it to a formula. Today, we're just going to focus on the 3 steps. So here's our next example. Find the slope of the tangent to the curve f at x equals 4 minus x squared at the point p, -3, -5. So here's p. I drew a graph for you. So again, step 1 is going to be we need our 2 points. So here's our point P. And then we have to figure out what our point Q would be. So again, Q is going to be a little bit to the right. So it's going to be, -3 plus h is going to be my x value, where h is just that tiny little bit to the right that we're placing Q. So then we want to find the y value that goes with x being -3 plus h. That's where we're going to find, I'll put it under here, f at -3 plus h by using our function definition there. So f at -3 plus h for us is going to be 4 minus, here we do definitely need brackets, -3 plus h squared. So that first step there was just using function notation, replacing x with -3 plus h. Now we've got to do some algebra. So I'm going to write this binomial out twice, like that. I'm going to use order of operations, so I have to square this binomial first before I distribute that negative. So I want to keep my FOIL in brackets here. So I'm going to do -3 times -3. 4 multiplications in there. So -3 times -3 is 9. -3 times positive h is -3h. H times -3 is -3h. H times h is positive h squared. And now, well, I can simplify a bit more inside the brackets if I want to first, because these are like terms that I can combine. Now what I want to do is distribute that -1 into the bracket. So that's going to be 4 minus 9 plus 6h minus h squared. Four minus 9 is -5. So all that work was just to get this y value that goes here. And it turns out that it's -5 plus 6h minus h squared. So the first step was to set up P and Q, and that's what we did. Just going back to the to the picture for a second, I always like to, especially if I have a picture, kind of look at my picture and make a prediction of my slope, so that when I get my answer for the slope of the tangent, I can test whether it makes sense or not. So I'm expecting a positive slope of a tangent and fairly steep, okay, if I look at my diagram there. All right, so that was step 1. Step 2 is to find the slope of the secant, so the slope joining P and Q, which you can call MPQ. And we just use the grade 9 slope formula to get that. So remember, the first point is going to be our x1, y1, and the second point is going to be our x2, y2. And then we'll go through and find the slope of the secant, simplified as much as we can. So at y2 is -5 plus 6h minus h squared minus y1, which is -5. So there's my bracket because I subtracted a negative, over x2, which is -3 plus h, minus -3. Everybody okay on that? Just putting in.
Yep. A-okay.
Okay. All right. So now we're going to look and see, we've got -5 minus -5. So when you subtract a negative, you're really adding. So here I have a 0 pair again. Those are gone. And same thing in the denominator, -3 minus -3. It's really add 3. So I've got 6h minus h squared in the numerator and just h in the denominator. And then we common factor h out of the numerator. And really one of the biggest reasons we're doing this is because we can't let h approach 0 if there's h in the denominator, just plain h, because as h approaches 0, the denominator approaches 0 and we can't divide by 0. So it's a really important step to be able to, I call this h in the bottom, the problematic h, to be able to divide out that problematic h before we take the limit. So now we can do that. And we're left with the slope of the secant in lowest terms being 6 minus h. So that's step 2. Step 3 is finding the slope of the tangent by taking the limit. So the slope of the tangent, so a big M or a regular sized M, and then tangent should be all subscript. I know it's hard to write that out, but it's important. The slope of the tangent is, so then again, the limit, and then subscript h approaches 0, subscript size, but it's written right below the word lim. The limit as h approaches 0 of, in our case, 6 minus h, the slope of the secant. Okay.
Do we have to, like, is it fine just having it just open beside limit, or will we ever have to like put that in brackets when we put it beside limit? Or?
Here, like, do we have to put 6 minus h in brackets?
Yeah.
Only if we're going to be doing limits just for limits in the next couple of days, John, and there'll be expressions like that involve multiplication. That's where you would have brackets.
Okay.
Okay.
All right.
And then, so then I'm going to put a little therefore, m tangent. So as soon as I take the limit, so I'm going to let h approach 0 now. So as h approaches 0, 6 minus h approaches 6, and there's my answer. So therefore, the slope of the tangent is 6. Reflect back to your diagram here. Fairly steep. Okay, 6 is steep for sure. That would mean I would go from my point up 6. 1, 2, 3, 4, 5, 6, and right 1. Can't fit any more of that in there, but my tangent would look, if I join those 2 points together, like that-ish. And that makes sense. Steep, right? Okay, there's our second example using the method that Newton came up with. So this was their very earliest kind of iteration of how calculus was going to go. Find the 2 points, find the slope of the secant, then take the limit to get the slope of the tangent. All right, our next one. Find the slope of the tangent to the curve y equals 2x squared minus 4x plus 3 at the point where x equals -1. So there's a couple of things different from this one that we did in the last two. So first of all, it doesn't show you the point on the graph. And it also doesn't give you the y value. So if I'm doing my first part here, I even need to know the y value that goes with x being -1. And I can see up here that it looks to be 9. But can anyone tell me how I can know for sure? How I can get the y value that goes with x being -1?
You can plug x, you can plug -1 into the formula.
Right. So I can think of y and f at x as being the same thing. I can find f at -1 here. So that's going to give me +1. So 2 plus 4 plus 3 is 9. So there's my p. Q again, you can see is going to be a little bit to the right. So it's going to have the x coordinate, so -1 plus a little bit. So -1 plus h is going to be the x value. And then to get the y value, I've got to do all that work here. So I've got to find f at -1 plus h using the formula, the definition up here. So 2, replace x with -1 plus h squared minus 4 times -1 plus h plus 3. So you can see why we did function notation in grade 11, how significant it is in calculus for sure. If you can square the binomial in your head, that's going to save you time, but I'm not going to assume that everybody can do that. If you can, go ahead and do it. So I'm going to distribute right here because I can. So -4 times -1 is +4. -4 times +h is -4h. And then here, I'm going to leave the 2 out front and do this FOIL before I distribute the 2. So it's going to be +1 minus h plus h squared. And again, these calculations take a while. Just be really careful with signs, and there's a bunch of different ways you can make tiny little errors that don't make it come out right. I've done it many times myself. I have to go back and say, okay, what did I do wrong there? And usually it's a sign, or I didn't multiply every part through by 2, something simple, but that's usually where it happens. So now I'm going to collect my constants. So 2 plus 4 is 6, plus 3 is 9, minus 4h minus another 4h is minus 8h, plus 2h squared. So that's going to be my y value up here. So 9 minus 8h plus 2h squared. So there's step 1. Look how much work that took just to get my P and Q set up. The more complicated the function, often the more time it takes you to just find that second y value there. All right, so now I'm going to find the slope of the secant, MPQ. And I'm just going to use the slope formula to do that. So y2 is 9 minus 8h plus 2h squared, minus in the slope formula, y1 is 9. x2 is -1 plus h There's a minus in the slope formula, -1. Then you see if you can simplify in the numerator. So I've got the 9 minus 9 adds up to 0. And then in the denominator, I've got -1 minus -1, which is really +1. So that also adds up to 0. And we're left with h. And then we're getting used to this. We should have an h that we can factor out in the numerator. So if you common factor h in the numerator, you're going to get -8 plus 2h, which gives me that h that I can divide out, the h in the denominator, giving me that the slope of the secant simplified as much as possible is -8 plus 2h. And then the third and most important step is to find the slope of the tangent by taking the limit as h approaches 0 of the slope of the secant, which is -8 plus 2h. So therefore, now we're going to let h approach 0. So as h approaches 0, -8 plus 2h approaches -8. Okay, and again, if h approaches 0, 2 times h will also approach 0. So the slope of the tangent ends up being -8. And then you're going to check back with your picture. Does it make sense that the slope would be negative? Yes. And fairly steep? Yes. Okay. So when you've got a graph, it's always good to go back and make sure it makes sense there. All right. Two more examples to go, then they're going to start getting a bit different. Instead of always working with quadratic functions here, we're going to go on to a reciprocal function or a hyperbola. That was one of the parents we worked with last year in grade 11, and you probably maybe did a little bit in advanced functions. So find the slope of the tangent to the curve y equals 4 over x plus 1 at the point where x is -3. All right, so let me look again here, -1, 2, 3. Looks like the y value is -2, but we can also check that using our defining equation. So f at -3 would be 4 over -3 plus 1, which is 4 over -2. Which is -2. Q is going to be a little, so here's P. Q is going to be a little bit to the right. So its x value is going to be -3 plus h. F at -3 plus h is going to be 4 over, so I'm replacing this x here with -3 plus h plus 1. There's still the plus 1 there. And I can, in this case, I can simplify the denominator by collecting the -3 and the plus 1 to give me -2 plus h. And that's as much as I can simplify. So that isn't nearly as much work as it was with the quadratics. So there's my 2 points set up, P and Q. All right, step 2 is to find the slope of the secant, the slope between P and Q, using the grade 9 slope formula. Okay. So y2 is 4 over -2 plus h. and y1 is -2. And x2 is -3 plus h minus x1 is -3. So we've got this 3-layer fraction here right now. I'm going to clean it up a little bit first. So I'm going to change this, subtract a negative to an add. And in the denominator, I'm going to take the -3 and the minus -3, which is a 0 pair. Okay, so the next step is, how do I simplify that? How do I write it as simple as possible? Does anyone have an idea of what I could do next to get rid of this 3-layer fraction, which eventually I'm going to want at most a 2-layer fraction?
Get a common denominator with the +2.
Good, so I want to get a common denominator in the numerator, okay? So right now in the numerator, my denominators are -2 plus h and 1, okay? So my common denominator is going to be -2 plus h. This is just within the numerator. Okay, so if I look here, this fraction already had -2 plus h as the denominator, so the numerator is going to stay the same. Here, the denominator was 1. I had to multiply the bottom by -2 plus h, so I'm going to have to multiply the top by -2 plus h. And that's just the numerator. It's still all being divided by h. So once you have a common denominator, you can, in this case, add the numerators. And I like writing this step in because it prevents us from getting signs wrong. Add our numerators over the common denominator, -2 plus h. And then also at this time, I like us to kind of combine steps here. Remember, this is a big fraction bar here. This is a divide. We're dividing by h, or you can think of h as h over 1. Dividing by a fraction is the same as multiplying by the reciprocal. So if I'm dividing by h over 1, it's the same as multiplying by 1 over h. Is everybody good with that step there?
Yep.
Yep, okay. All right, so we're going to keep going here. So I'm going to look at the numerator first here. Multiplying the numerator by 1 doesn't change anything, but I do want to distribute the 2 now. So I've got 4, plus positive 2 times -2 is -4, plus 2h. Over the denominator, though, if I'm multiplying h by -2 plus h, I might want to put my monomial term out front and then use brackets to show that I'm multiplying by -2 plus h. Knowing that this h here is the one I call my problematic h, the one I can't let h approach 0 if I've got that h there in the denominator, because then the denominator is approaching 0. So that's the one I'm hoping to be able to divide out using some kind of algebra as we go through. So I'm still not done simplifying the numerator, because now I'm really lucky. I've got 4 subtract 4 is 0. So I've got a 0 pair there. So I'm only left with 2h in the numerator. And in the denominator, I've got h times -2 plus h. So does anyone see what I can do to simplify?
Yeah, we could just divide out the h from the top.
Yes, nice. We can just divide out those h's. Perfect. So now the slope of the secant is 2 over -2 plus h. All right, awesome. So now we're ready for step 3, which is to find the slope of the tangent. So the slope of the tangent is going to be the limit as h approaches 0 of 2 over negative 2 plus h. Now I'm actually going to take the limit. So I'm going to let h approach 0. So as h approaches 0, the numerator 2 stays the same. And the denominator, negative 2 plus almost 0 is negative 2. So the denominator approaches negative 2. And then if I divide those, I get negative 1 for the slope of the tangent. And let's look back at our picture and see if that makes sense, which is going to look really good here. So is tangent slope being negative? Definitely. Being negative 1 means down 1 over 1, down 1 over 1. And if I draw it in, it should look perfect as a tangent at point P. And it does. Negative slope of the tangent is negative 1. All right, so that was one that involved finding a common denominator. So far we've done common factoring to get rid of the problematic h, and we found a common denominator to help us simplify a fraction and divide out that problematic h. We're going to look at one more way. And then these kind of ideas are going to be repeated tomorrow, even though we're going to use formula instead of like the 3 steps. All right, our last example, one of my favorites. So find the slope of the tangent to the curve f at x equals the square root of x plus 3. So it's a square root function, if you remember from grade 11, at the point 1, 2. So they give us p. Here's P. So our first step is we need P, 1, 2. And then we need to pick a point Q right next to P. And its x value is going to be 1 plus that little bit h. And then we have to find the corresponding y value. So we want f at 1 plus h. Here's our defining equation. So it's going to be the square root of, replace x with 1 plus h plus 3. And then we can combine the 1 and the plus 3 to make 4 plus h. Is everybody good? That's as simple as we can make that. Because of the add here, we can't take the square root of 4, which sometimes is tempting to do, but we're stuck with the square root of 4 plus h as our y value. This one's fun. It's something you haven't done before, probably, or likely in many cases, so it's kind of cool. All right, so there's our first step, is to get P and Q. Second step is to get the slope of the secant, so MPQ using the slope formula. So y2 is the square root of 4 plus h minus y1 is 2, x2 is 1 plus h, x1 is 1. All right, and there isn't any simplifying I can do in a moment in the numerator, but I know there is in the denominator, so I'll go ahead and do that. 1 minus 1 is 0. So it kind of looks like we're stuck here, but if we went and took the limit now, we couldn't let h approach 0 because then the denominator would be approaching 0. So there must be something we can do, and there is, and it's really cool, and it's called rationalizing the numerator by multiplying by the conjugate radical. That all sounds very complicated. It's actually very cool. So we're going to do a common kind of math, I won't say a trick, but we're going to multiply by 1. Multiplying by 1 doesn't change anything. And we're going to do it in a very smart way that's going to help us free up this h under here that we desperately need in order to divide out that problematic h in the bottom. We're going to do it by multiplying the top by what we call the conjugate radical. The conjugate radical is always really easy to make. It's going to have exactly the same radical part. If this happens to be a minus between the radical part and the plain number, or we could have two radical separated as well, the sign's going to be opposite. And then the second part's going to be exactly the same. Okay, so this here is called the conjugate radical. Radical, if you remember from grade 11, means the square root symbol, positive square root symbol. And root 4 plus h plus 2 is called a radical expression. It happens to be the conjugate radical of root of 4 plus h minus 2. But we want to multiply by 1, or think about whatever we do to the top, we have to do to the bottom as well. Otherwise, we've changed the value of the expression. All right, it's going to get exciting. Okay, I'm excited. All right. So we're thinking of this as a binomial. It's got a radical term and a plain number, and this is also a binomial. And we want to multiply them together, and the way we're going to do that is to use FOIL. So we're going to multiply first by first, first by second, second by first, second by second. So we're going to carry out those 4 multiplications. All right. What is the square root of 4 plus h multiplied by itself? If I multiply these two together, what do I get and why?
You get 4 plus h.
You do. Why?
Because if you multiply a square root by itself, you get rid of the square root.
Right. So you multiply a square root by itself. I'm doing that off to the side here, which is another way to do that is to write it as the square root squared. Squared does undoes square root, so you're just left with 4 plus h. Awesome. Okay. There's the first multiplication. The second one is the square root of 4 plus h times positive 2. So that's going to be, I'll write it as positive 2 root 4 plus h. So I'm just taking this and multiplying by positive 2. So there's my first 2 multiplications done. Now I'm doing the green ones, the lower ones. Negative 2 times root 4 plus h is minus 2 root 4 plus h. So that's my negative 2 multiplied by the square root of 4 plus h. And then negative 2 times positive 2 is negative 4. So I multiplied the tops together using FOIL. The bottoms, I'm not going to do that though. I'm not going to expand. I'm just going to show it as that problematic h multiplying by the root of 4 plus h plus 2. So if I want to clean the top up a bit, does everyone see the 4 and the negative 4? Add to a 0 pair so I can cross these off. But what's really cool is these two right here.
It ends
What
up
do
almost,
those? Yeah, do they
it
add up
ends
to
up
0,
almost like
guys?
a difference of squares.
It does. It ends up being a difference of squares. So we have plus 2 root 4 plus h minus 2 root 4 plus h, which adds up to 0. So all I'm left with in the whole top is h. And in the bottom, I've got that problematic h times the root of 4 plus h plus 2. So now I can divide those h's out. And what's left on the top, remember, is a 1. So I don't want you to forget about the top. There's really a 1 left there after you divide out the h. So MPQ is going to be 1 over the square root of 4 plus h plus 2. So that's our slope of the secant. And we used rationalizing by multiplying top and bottom by the conjugate radical there. New, totally new for us, or for most of us. All right, step 3, slope of the tangent. Slope of the tangent is the limit as h approaches 0 of 1 over the root of 4 plus h plus 2. Okay, this one takes maybe a little more thought here. So as I let h approach 0, the numerator is going to stay the same as 1. What's going to happen to the root of 4 plus h as h approaches 0? Well, it's going to approach just the root of 4. And then the plus 2, that's not affected by h approaching 0. It's just going to stay there. And then lucky for us, we can actually, the square root of 4 is a nice number. It's 2. So if I go over here, I finally get that the slope of the tangent should be 1/4. And then let's look at our picture and see if it makes sense to have a positive, not very steep slope of a tangent at point P. So if we go up here, so my rise is 1, my run is 4, 1, 2, 3, 4. Reverse it. There's my tangent of 1/4. And makes sense? Everybody good? That one's one you'll definitely want to practice. I have 4 practice questions for you. They're not from the textbook. I just made them, so you should have them in the left to do. I'll post solutions for you. So our success criteria for today then are that you can find the slope of the tangent to a curve at a specific point using the underlying ideas behind calculus. Understand what is meant by the statement, slope of the tangent is equal to the limit as h approaches 0 of the slope of the secant. Make sure you understand that h can get infinitely close to 0, but never actually equals 0. And then along with that, you understand that if you divide by 0, it's not defined. Okay, I'm going to stop the recording and then talk to you for a minute or so, and then we'll be done for today.